Arc length. When you have a little slice of a circle, say that that's an angle of theta, then that's going to give you something like that. The length of the edge of that, that's your arc length. And I think we probably get it from physics, but we use the letter S to denote the arc length. S, in my experience in physics, always meant distance. And it means distance now. It's just the distance on that little portion of the rim of a circle. And there's a formula for it, which is pretty simple. Let's assume that the radius of your circle, or this angle that you're working in, the portion of a circle, is r. And the arc length is simply r times theta. S equals r times theta. But there's a catch. All right, and the catch is the part that's going to get everyone. Theta must be in. Anyone fill it in? Radians. Yeah, has to be in units of radians. If you put it in degrees, it's not going to work. In fact, I'm hoping that you'll realize you made a mistake if you put it in degrees. So let's do a couple example problems, starting with problem number 72. 72 is kind of a friendly one because we are going to start out with units of radians to begin with. So let me pull that over here for us. There we go. So I want to find the length of a piece of arc, a stretch of arc. If the radius is 6 feet and you're dealing with an angle of 2 radians. Now 2 radians is pretty big. That's like about a 142 degree angle. Not quite, close to 143 degrees. It's in there. But the arc length is going to be pretty simple for us. S equals r times theta. In this case, it's going to be, 6 was the radius. 6 times 2 gives me 12. But let's not forget about our units. It's 12. Well, the radius was in what units? Radius was in units of feet. 6 feet. So the length is going to be units of feet. Under what circumstance would I put feet squared? I'm going to use feet squared for the units. Yeah, if you're talking about area. If you're talking about area, then it's in square units. If you're talking about volume, then it's in cubic units. But this is just the length. It's how far you would, walk if you're going from one point to the next along that path. So now, more realistically, you're going to get a problem like number 78, which gives you an angle of 120 degrees and a radius of 3 meters. R equals 3 meters. So 3 meters, probably kind of close to 10 feet. If you're walking on a circle radius of 3 meters, how far would you have to walk to get an angle of 120 degrees? So something about like this. We're trying to find a measure of that. Where do I start? Trying to find S. So 120 degrees, 3 meters. Well, the big thing that you have to do is you have to convert theta into radian degrees, to radians. Because if you don't, then it's going to be way wrong. Let's do that first. So 120 degrees, what should I multiply to convert that to radians? I know that goes back before our break, so maybe it's a little foggy. Pi over 180. Good. So the units that you want to cancel go in the denominator. And cancel indeed they will. So Units of degrees cancel. Leaves you 120 over 180. That's 2/3 pi. Yay. So this is going to work out really nice. We're going to calculate S equals R times theta, which is going to be 3 times 2/3 pi. And something else pretty nice happens. What else happens that's pretty nice? Yeah, the 3's cancel. So you're just left with 2 pi. And unless I ask you for a decimal value, it's fine to leave it like that. 2 pi is going to be about 6.28, but yeah, 2 pi is like that. There is something that's missing, though. Meters. You need the units. So the unit there would be meters. Yay. Let's do another problem, but not quite like this. Sometimes we want to know the area of this little sector, and that's going to be a different formula. Yeah, question? There was no pi for our angle, right? So the angle was just 2 radians. It wasn't 2 pi radians. It was just 2 radians. So I didn't have any pi here. So it was just exactly 12. Whereas for the second one, in our angle, we ended up with units of pi, and so I just left the units of pi. I mean, sometimes, you know, you might want an actual decimal value, and that's fine. You can do it out here, 2 pi, 6.28, and then choose as many decimals as you want. All right, but I just felt it convenient to leave it in units of pi here. But appreciate the question. Thank you. All right. So let's do another one here. And this time we're going to find units of area. And the formula for the area of this sector is 1/2 r squared theta. Any guesses about theta? What special condition might pertain to theta? Other one. Yeah, there you go. Has to be in radians. So kind of like its cousin formula over here, theta must be in radians. So, okay. So we'll keep that in mind and look at some other problems. Let me grab which one we want to do next. I think we'll do problem number 86 next. All right. So here we got r equals 3 meters, and theta is a familiar 120 degrees. Well, let's kind of cut to the chase, right? We already calculated this one. That's going to be 2 pi over 3, and that's what we need to use in terms of figuring this out in units of square meters, figuring out our area. Area is 1/2 r squared theta, which is 1/2 times 3 squared times 2 pi over 3. Now, I'm not sure how you want to work on this, but I think I'd probably cancel out a couple things here and there just to make my life easier. Do you see anything that can cancel? All right. Squared here. Let's get rid of one of those there. That's good. Nice. And the other thing they can cancel is this 2 and that 2. Doesn't leave us with much, does it? What's left? 3 pi. 3 pi. There's one other important thing that we need here. Meters squared. We're talking about area, so we have to have square units for area. So there you go. Meters squared. Let's do one a little bit different. Same formula here. It's just we're going to use it in a different way. Let's kind of work backwards. Are we okay with problem number 86 there? All right. We'll take a step back and look at problem number 84. Let me put that up here for you. Okay, so this one's a little different. They give us the area as 8 square meters, a radius of 6 meters, and they ask us for theta. Okay. Well, let's write down what we know and what we don't know and see if we can't figure this out. So, problem number 84. R is 6 meters. Area is 8 meters squared. And we need to know what theta is. Theta is unknown in this. That's okay. So let's write down a little formula. Area is 1/2 r squared theta. We know area is 1/2. 1/2 times 6 squared times theta. Help me solve this. What would you do? Oh, nice. 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 Yeah, that's really cool. I'm going to take a little less abstract approach. I mean, there's nothing wrong with what you did. Yeah, if you wanted, in general, theta is going to be 2a over r squared. But since we got the numbers here, let me simplify this. 6 squared is 36. Half of 36 is 18. Thank you. If we solve for theta, 8 over 18 equals theta, or theta equals 4/9. Now, 4/9 is in what unit? It's in radians, right? Now, remember, 1 radian is about 57 degrees. But what's 4/9 radians? That's kind of a weird unit. You know, and it's not easy to relate to. So maybe there's kind of a follow-up to this. Let's convert 4/9 radians to degrees. So let's multiply by something. What would it be that we're going to multiply by? Is it 180 over pi or pi over 180? Which one is it? Well, 180 over pi. So you were right. 180 over pi. The units that you want are going to be in the numerator. So the units we're trying to get rid of is radians, even though there's no pi to cancel out. That's okay. You know that 4/9 is 0.44444. It's less than 1. So you should have an angle that's less than 57 degrees someplace. In fact, probably less than half of that. And let's see what we get here. Actually, you could do some cancellation. 9 goes in there 20 times. You'll end up with 80 divided by pi. So let's do that. 80 divided by pi should be about 25.46 degrees. So a little different spin on that. Okay. Any thoughts or follow-up on Yeah, that's okay. Well, let me add a little step here. 6 squared is 36. 1/2 of 36, that's where I got the 18. Okay? Yeah, I just didn't show that extra step. My bad. Selena? Well, that's your answers in radians. It's just that even for me, and I've been teaching this class since 19 mumble, I wouldn't look at 4/9 radians and go, oh yeah, that's around 25 degrees. I just can't relate to it. So I just put it in a more comfortable degree. On a test, I'd probably have to say, if I wanted it in degrees, I'd say convert your answer to degrees. Well, there's nothing wrong. In fact, if you looked up the answer in the back of the book, they'd probably have 4/9. All right, because that's your answer, and it's in radians. And don't just put a pi there because it's in radians. If it doesn't come out in the math, it's not there. So. Yeah, and like I said, if I want the answer in degrees, then you'd have to do that extra step. But no, this one doesn't really require that. Yes. Here at the end? Sure. So, do you agree that we're multiplying by 180 over pi? Because you want to get rid of units of radians, and you want to end up with units of degrees. So the units you want to end up with are going to be in the numerator. So that puts the 180 in the numerator and the pi in the denominator. There's really no cancellation with the pi in any way. That's okay. But 9 goes into 9 once and into 180 20 times. 4 times 20 is 80. So you end up with 80 over pi. And if you noticed, when I calculated that on my calculator, that's exactly what I typed in. It's 80 over pi. So I really appreciate the questions. They're helpful to me, and they're helpful for the video, so please keep them coming. Is there anything else on that one? Brian? Not for these, but the mode is going to matter soon. It's going to matter really soon. So, yeah. Now, the nice thing about the TI-84, the nice new ones, is that it tells you what mode you're in, radians or degrees. Now, up till now, our calculations haven't required us to change that, but later on, they will. We're going to have to go back and forth and practice that. All right. Let's do one more here, or actually one more formula. These formulas, by the way, seem to be the ones that get forgotten the most on exams. These two, so might want to put them down, keep them around. But I'm going to take that formula, our first one. So S equals R times theta. Let's start out with this one, and I'm going to do the same thing to both sides. I'm going to divide by t. And by that, I'm thinking of dividing by time. Now, earlier I said that S usually stands for distance. What's another way of thinking of distance divided by time? What's that give you? Anyone remember? Distance divided by time? Yeah, it gives you your rate of speed. Your velocity is, yeah, it could be your velocity, all right? So we'll call that V for velocity equals the radius. And here's the cool thing. You're going to learn a lot of Greek letters in this class. So we've already seen theta. Let me give you a new one. It looks like a W, but it's really an omega. And so V is your linear velocity. And R, well, what was R in this original formula? Radius. And omega is the angular velocity. That's how fast your angle is changing in units of time or degrees per unit of time. Let me see if I can't come up with a quick little demo on that. Let me see here. One of the things I use a lot is Desmos, and I think I've got something here that can do that. Sine and cosine animation. All right. So, yeah, pretty cool. Ooh, ah. Feel free to ooh and ah, right? Remember, it's supposed to make me look good? All right. All right. It's a pretty weak sauce. All right. But take a look at this little point that's moving around on the rim. It's connected to the center of our circle by a line, and it's that line that keeps on moving around. Now, the rate at which that changes is your omega. That's your angle per unit time. So if it takes, say, 6 seconds to go all the way around here, then your value for omega would be 2 pi, which is all the way around once, in 6 seconds. So 2 pi divided by 6. That would be the angle for the measurement for omega. So let's see if we can't put that together into a problem. And the one I want to start with is problem number 92. Always puts me in mind to remember an old neighbor of mine. In fact, he was a World War II veteran, which is really cool. He used to build his own pendulum clocks. And he would make them completely by hand and out of wood. So everything all the way down to the wooden dowels and pendulums, everything was made out of wood. They were really exquisite. Okay, so problem number 92. Oops. Let me just check something here. There. All right. Might be a little snafu in my video, but it is what it is. Problem number 92. A pendulum swings through an angle of 20 degrees each second. If the pendulum is 40 inches long, how far does the tip move each second? So let's see what we got, see what we know, and figure out what we don't know. So what we're trying to figure out is the velocity of the tip. How fast is that moving? So that's going to be the right-hand side of this equation. Let me write down for us the things that we know. So, problem number 92. The first thing we know is that omega is 20 degrees per second. That's how fast it's swinging. And they gave that to you. We also know the radius. Radius was 40 inches. Okay, and we're trying to calculate the velocity. And the velocity is simply r times omega. So that's not too bad. But there's probably a catch here, right? You know what the catch is? This unit has to be in radians per unit time. Just like when we use this formula back here, that had to be in radians. It has to be in radians now. So let's convert 20 degrees to radians. Natalie, what am I going to multiply to convert this to radians? Perfect. Pi over 180. Units of degrees cancels out. In fact, the 20 goes in here exactly 9 times, so I'm left with pi over 9. So I'll write that as pi over 9 per second. That's our angle. That's the rate at which our angle is changing. If I then plug it into my formula, I get 40 times pi over 9. And, well, got to do a little bit of arithmetic here. 40 pi divided by 9. 40 pi divided by 9 gives me about 13.96. 13.96, we'll call it. But let's think about the units of the answer. The units of the answer are basically how fast that tip is moving. I haven't put them yet. That's what I'm asking people to think about, is the units. So what are the units going to be left? Well, nothing happened to the units, right? Nothing. The inches are still here. And this is in time per second, right? So inches per second. That's our final answer. And that makes sense because inches per second is a velocity, or it's a speed. I should say speed if I want to be very accurate. It's not a velocity because it doesn't have a direction. But inches per second. Nice. Okay. Let's do one more like this. Before I move on, how are we looking with that last one? Okay. I got a question for you, kind of a trick question. As you're at your desk there, how fast are you moving? That's actually pretty spot on. That's close to what I was thinking of. Let's figure out how fast we're moving. And let's think big. Not just the Earth moving around its axis, but the Earth moving around the Sun. And we're actually moving surprisingly fast. I wish I could give freaking flyer miles for how far we're moving. All right. So we'll go back to our formula. Velocity is going to be r times omega. Now r, unless you're an astronomer, you probably don't have this off the top of your head, so I'll help you out. Is 93 million miles away. Yeah, there actually is one in the book that's similar to this. I don't know where it is, so we'll just do this one. So now the big thing is we got to figure out omega. How fast is our angle changing with respect to the sun? Funny thing is, you know it, but you just don't know it. So, how long does it take us to go once around the sun? A year. A year to go all the way around the sun. So that's going to be the denominator divided 365 days. But what's the angle that we go in 1 year? And I want that angle in radians. Is anyone? 2 pi, right? It's 2 pi per year. 2 pi for 365 days. So, okay. Well, let's see here. So our velocity is going to be 93 million times 2 pi divided by 365 days. So, okay. Now, a little trick here for you. You can put in numbers in scientific notation. So this is 93 followed by 6 zeros. So if I type in a 93 times 10 to the 6, well, the cheating way to do that is you type second, bless you, and then the comma, and put a 6 there. 93E6. That's 93 million. Times what? Times 2 pi. So times 2 pi divided by 365. Wow. There you go. So, let's see. 1.6 million miles. Now let's keep track here. The units here are miles, and the units here are days. Did those units cancel out in any place? No. So it's just miles per day. Let's see. Day. It's a great question. It's a great question. Before I answer that, let me just make sure we're okay with where we're at here. Okay. I don't see any big complaints. A great follow-up question is like, all right, Well, I don't relate to miles per day. What do you relate to? What distance or rate? Miles per hour, right? So, my trick in this class today has always been to multiply by 1. The units I want to get rid of are down here in the denominator. So I want to get rid of days. So 1 day, I want to have units of hours, right? 1 day is 24 hours. So if I multiply like this, then I get some nice cancellation. Units of days cancels out, and I'll take my answer on my calculator and divide by 24. So let's take that and divide by 24. Oops, 24. So 67,705 miles per hour. So if you multiply that by 3, about 200,000 miles during the length of this class. Wow, not bad. Let me divide by 3. Now there's 3,600 seconds in an hour. So if I divide that by 3,600 seconds, you're moving at about 18.5 miles per second. So, woohoo! That's pretty fast. There you go. List of accomplishments. Yeah, put that on your resume. Huh. I can travel 18.5 miles per second. All right, cool. Let me give you some homework, and that should take care of things for section 2.1. You're not going to need a minute to do the homework, so why don't you take a quick break? I'll see you in 5 minutes.